Okay, here we have the situation with question 7, and I've started putting in some of the forces. Here we have particle A, which has a mass of 0.3 kilograms, so its weight acting vertically downwards is 0.3 g. And here's particle B, which has a mass of 0.2 kilograms, so its weight acting vertically downwards is 0.2 g. There's a normal reaction between A and this rough surface here. I'm going to call that one R, that's the normal contact force. And there's also the normal contact force here between B and the slope. And remember, the slope is smooth, so I'm going to call that one R1. Okay, so we're told that they are connected by this piece of string. Now basically this piece of string means that there is a tension in the string which is acting to the right on A, the way I've drawn it, so let's just call that T. And at the same time, the tension is acting on B to slow it down. So the tension is acting up the slope on B. Okay, what other forces are acting? Well, we are told that the coefficient of friction between A and the slope is 0.4. And we're also told that the system is released from rest and both particles start to move. Now, just looking at the situation here, it's fairly impossible that A is going to move to the left. So in other words, it's going to move to the right. The whole system is going to accelerate so that B moves down the slope like that. That's the acceleration of B. And the acceleration of A is going to be in that direction. And because we're told that the particles are moving and that the slope here, that the table here is rough, the frictional force acting must be so as to oppose the motion of A. In other words, the frictional force is going to be acting to the left on A. Let's just draw that in. Okay, so here's our frictional force, and that frictional force we know is going to be at its maximum because we've got motion. So I'm just going to write here F max. So those are all the forces which are acting in this system. The next thing I'm just going to put on are some of the angles here. We're told that this angle down here is 70 degrees. I'm just going to write that in. So that's 70, which means that this angle here must be 20 degrees. And I usually just put in some others. I'm just going to continue this straight line. So it's this one line, and we've also got a 70 degree there, just in case we need it. Okay, first of all, I'm going to look at A, and I'm going to work out F max. Now, if we look at A, so let's just do this for A, I can see that A is not moving upwards, it's not moving downwards, so the forces acting up must equal the forces acting down. So R must equal 0.3 G in the usual way. And F max then, because we know that F max is equal to mu R, we know that F max then is going to be this mu. Well, we know that mu is 0.4, so it's going to be 0.4 times 0.3 G. So F max is 0.12 G. So I'll put that on the diagram. Okay, so 0.12 G. Okay, what I'm now going to do is I'm going to do Newton's second law on A. And in fact, I'm going to do in the same way as I normally do with connected particles. I can do Newton's second law on both particles separately. So let's have a look at A. What's happening? Well, we've got this force T pulling it to the right, and we've got F max pulling it to the left. The direction of the acceleration, though, is to the right, so I'm going to use Newton's second law to the right, taking to the right as positive. So to the right, we've got T. Against that, we've got F max. So T minus F max, so that's the resultant force on A, the F part of it, is equal to the mass, well, that's 0.3 times the acceleration, so that's 0.3 A. And we've just found out what F max is. F max is that 0.12 G, so F max minus 0.12 G is equal to 0.3 A. Now there's nothing I can do with that, there's two unknowns, the A and the T, so I'm just going to leave it as it is for now. Okay, now let's do Newton's second law on B. And we can see that B is accelerating down the slope. Let's have a look at the forces which are acting on B. Tending to make it go down the slope is a component of the weight acting in this direction. And that's going to be 0.2 G cos 20. So going down the slope, that's the positive direction, is 0.2 G cos 20 degrees. And acting against that is the tension, so that's going to be negative, and that's going to equal the mass of B, well, 0.2 times its acceleration. And again, I'm going to just call that one equation 2. What I can now do is add those two equations together. So I'm now going to do 1 plus 2, and I can see that by doing that I've got t and minus t. Those are going to disappear, and all I'm going to be left with are these two. So that's 0.2g cos 20 minus the 0.12g, and that is equal to 0.2a. And if I work that lot out, a comes out as 1.3315 blah blah blah. So a is equal to 1.33 meters per second. And to work out what t is, I'm just going to put t, or I'll put it back into this one. So t is going to be 0.12g plus the 0.3. Now I'm going to use 1.33 here for t rather than the exact value, because remember that exact value of a isn't actually exact because we've used g, which has been rounded. So if I put 1.33 into there, t comes out then as 1.58 newtons to 3 significant figures. Okay, part 2. We're now told that the string breaks when both particles are travelling at 1.5 meters per second. And it's very important to realise that when the string breaks, effectively the tension on both of the particles has now disappeared. And the question asks us to find the distance travelled by particle A before it comes to rest. Okay, so let's just have a look at particle A and the forces which are now acting on particle A. Well, we've still got its weight acting vertically downwards, that's 0.3g. We've still got the normal reaction acting upwards. Tension that was making it go to the right has now disappeared, and all we've actually now got, because it's still moving, is F max. And what we've got to realise here is that F max is going to be exactly the same, because it's still only moving horizontally. The force up and the force down will still be equal, so R will still be 0.3g. The coefficient of friction hasn't changed, so that F max is still going to be 0.12g, same as it was before. So let's find the acceleration then of particle A, and I'm going to use Newton's second law to the right because it's still accelerating to the right, but acting to the right we've actually got nothing. So Newton's second law to the right, nothing to the right, minus our F max, so it was the tension before to the right, now it's just nothing, is going to equal the mass, well that's 0.3 times the acceleration. As we've said though, F max is the same as it was before, that's the 0.12g, so minus 0.12g is equal to 0.3a, and a then comes out as minus 3.92 meters per second. I'll write it like that. Okay, so what we've now got is we've now got A accelerating to the right at minus 3.92 meters per second. In other words, A is decelerating, as you would expect, and it's going to come to rest. And we want to find the distance that it travels before it comes to rest. Well, we're told that when it starts this part of the motion, it's traveling at 1.5 meters per second, so that's when the string breaks. The final velocity is 0 because we're finding the distance until it stops. The acceleration is minus 3.92, and then S is what we're trying to find out. So I'm going to use v squared equals u squared plus 2as. So from that, 0 is equal to 1.5 squared plus, let's put it here, 2 times minus 3.92 S. And if we work that lot out, S comes out as 0.2869. So S is 0.287 meters to 3 significant figures. Okay, the last part of the question asks us to find out the distance that's been travelled by B in the time that in the time it takes from the string to break for and A to come to rest. Now obviously in that time, because they're not connected, B is going to be doing something completely different. So what we're going to do is we're going to work out the acceleration of B and then look at the distance that B travels in the time that it takes A to come to rest. First of all though, we can work out the time that it takes A to come to rest, and we're going to use the same information that we've got here, and actually all we need to do is find T, so I can just use V equals U plus AT. So I know that 0 is going to equal 1.5 minus 3.92 T. And if I work out T from that, T comes out as 0.3826 seconds, and I'm going to store that in my calculator because what we're trying to find now is the time that is the distance travelled by B in that same time. So our first thing to do there is work out the time that we need. So let's have a look then, and we're going to do now Newton's second law for B. So let's just draw a quick diagram to show what's happening for B. Here's B on its slope. The T that was holding it back is no longer there. What it does still have though is its weight, which is the 0.2 g, and it's still got its normal reaction here. So I call that R1. And this angle here, remember, was 20 degrees. So if we do Newton's second law for B, B is accelerating down the slope, obviously not the same acceleration as before because it's now not connected to A. So Newton's second law down the slope, well, the only force acting on this one is B, isn't it? The only force acting on B is the component of the weight down the slope, which is 0.2 g cos 20 degrees. So the minus T has now gone, and that is equal to the mass times the acceleration. Well, if I divide both sides by 0.2, it means that A is just g cos 20, and that comes out as 9.208 meters per second. So that's the acceleration of B down the slope. Now it becomes quite trivial. We know that the initial velocity, this is the period that we're looking for, was 1.5. That was when the string broke. Final velocity we neither know nor care. The acceleration though is 9.208 down the slope. The distance travelled, well, that's what we're trying to find, and we know that the time, because it's the same as the time taken for A to come to rest, is what we found up here. So that's the 0.3826 seconds. So I can now use S equals ut plus half AT squared. Plug everything into that. It helps if you've stored it all in the memory of your calculator. So that's the 1.5 multiplied by the 0.382 plus, and then it's going to be 0.5 times the 9.2 times the 0.382 squared. Don't forget to square that. The distance then comes out as 1.248. In other words, 1.25 meters.